Cool. So let's understand the next topic, which is HDFS architecture. We'll be first understanding different modes of Hadoop configuration. Okay. So there are three different ways you can actually install Hadoop. One is called standalone mode, one is called pseudo distributed mode, and one is called fully distributed mode. So in standalone mode, basically all Hadoop services run in a single JVM on a single machine. So let me just draw it here. It will be something like this. In a standalone mode, all the Hadoop services run in a single JVM. This is my JVM where all the Hadoop services like master, slave, and there are some other processes also which runs on the same JVM in a single machine. That's why it is called a standalone mode. So this is a standalone mode where you have one physical machines and under one JVM all the services are installed. In a pseudo distributed mode, I will have multiple services running in multiple JVMs like this. These are all JVMs where you have master process running, slave, and there is another processes running. I'll be telling the name of all these processes later. This process means nothing but they are programs. So they make up the Hadoop framework, or they are the programs which does Hadoop job. So they are running in a separate JVMs in a single physical machine. This is a pseudo distributed mode, and the guide which I have given you is actually having a setup which helps you to achieve pseudo distributed mode. So you will have a one physical machine, but still all the processes will be running in a separate JVM, so that when you do any Hadoop operations, when you execute any Hadoop job, it will be basically talking to each other in a distributed manner. And then there is something called fully distributed mode where you have master slave architecture, right? This is the fully distributed mode where you have multiple physical machines, and it's just like a production environment where you are having multiple physical machines, and all of these machines will have different processes running. So master will be running here in a separate JVM, slave will be running in these JVMs, and so on and so forth. So basically, this is how you define a fully distributed mode setup. This is pseudo distributed and this is single node cluster. Okay. So that's the three different ways of configuration. We will be working on this setup, which is pseudo distributed mode, because we have one physical machine. This is how you can see the architecture. Okay. The Hadoop architecture and all the processes running inside this. Basically, we will be now going forward name these processes. Okay, I'll be actually giving a name to this. So you have a master machine, right? This is my master machine, and these are all slave machine. It's a master slave architecture, and a master machine will have certain process or programs running for Hadoop, which is called name node and job tracker. Okay. It's called name node and job tracker, and the slave machines will have something like data node and task trackers. These are the services running here. There is also one more machine which is called secondary name node, which will be running separately, which is doing some other stuff. So I'll be explaining you the functionality of each of them. All right. And as we know, if I am storing a file of 128 MB size, and by default if the 64 MB size is there for every block, then when you store that file in HDFS, it will be divided into two blocks and they will be stored like this, and the metadata will be stored with the name node. So this is a very high level overview of the overall architecture, and that's how you can visualize the process. Okay, now here now what we will do is here, if you observe here, there is a name node. There is also secondary name node. Okay. And there is data node. All these three processes will basically do the HDFS operations. Okay. They are the ones who helps you to do store and retrieval of storage of the distributed data as well as retrieval of the data in a distributed manner. So these three processes makes up HDFS component, and these three processes are nothing but three Java programs. Okay. Then there is job tracker and task tracker. These two makes up. These two basically helps you to do processing of the big data using MapReduce. So they are part of MapReduce framework. These two processes. All right. That's how basically. So as we understood, HDFS and MapReduce together forms Hadoop. So that's how we can visualize all these processes running together in this cluster. Okay, and we'll be going step by step and understand each of these components thoroughly. So first we will start with HDFS, and we'll be understanding the entire HDFS architecture, and how do they work to each other. Everything we'll understand in a step by step manner. One more important thing, in the latest version of Hadoop, we will basically have YARN, name node and data node. NN means name node, DN means data node. Okay, so the latest version of Hadoop contains something called YARN. Okay, apart from HDFS and MapReduce. What is the use of YARN? I have explained you on the first day, generic use case, so that any distributed processing framework can be used to process the data. Okay. But we will be also understanding little bit more on that later. So I'll park it aside for that purpose. But right now, with introduction to YARN now, there is no more job tracker and task tracker. Now there is something called node manager and resource manager. These are the two processes which has encapsulated job tracker and task tracker functionality. Okay, so that is why you have now these 5 processes running in your machine. Name node, data node, secondary name node, node manager, and resource manager, which makes up the latest Hadoop cluster. Okay, so this is the overall overview of all the processes as part of Hadoop architecture. When you install Hadoop, you should be having these 5 processes running in your machine, in your cluster. If it is running, that means your Hadoop is working fine. Otherwise, there is some issue. All right. Here we'll be talking now about HDFS architecture first. Okay. So what we'll be doing is we'll be basically first take one component on Hadoop, which is HDFS. Then we will take MapReduce, and then we will also understand YARN. Okay. And each of this component will be doing hands-on exercises. Once we complete this, you will complete your core Hadoop. That's how I'll be following up. And I'll be doing a lot of hands-on practicals on each of these components so that you will get clarity on how to use all of these components. Okay. So I'll repeat one more time. Okay, so that everybody can understand it, easily. So in the master, you have a name node and resource manager, and in the slave you have data node and node manager. These are the 2 processes running in each and every slave nodes. And there is secondary name node here. That's how you can visualize it. That's it, done. Now I'll be cool. So now we'll talk about HDFS, which is the first core component of Hadoop, which deals with storage layer, right? So it helps you to store data in a distributed manner. So in HDFS, as we understood, there are 3 processes, right? Name node, data node, and secondary name node, correct? So there will be, in a master, there is a name node running. Here, all the slaves will have a data node running, right? Data node will be running in a separate JVM. Name node will be running in a separate JVM. And of course, there is one more machine which has a secondary name node running. Okay. So we will now not even focus about YARN or MapReduce right now, right? So we don't really need to talk about those processes right now. We'll just talk about these processes which makes up HDFS, and we'll first understand how a data can be stored and retrieved from the HDFS. All these machines, I will not talk about anything where you have intra-cluster communication, because that's what we discussed on first day, that there is, in Hadoop you don't have that option available. Cool. Now let's understand step by step. So as we know, master will remember what? Metadata information, that this file is divided into this many blocks and it is stored in, and each block is stored in different machines like data node 1, data node 2, and so on and so forth. So this is the information which masters remembers: file to block mapping and block to data node mapping, and data node only stores the actual blocks. Another important thing is, if you have another file, let's say file 2, which has block P and Q, then it would be stored here, like P will be stored here and Q will be stored here, right? So this guy in master, you will have that information also stored, that file 2 will have 2 blocks P and Q, and it is stored in which machines? DN1 and DN2, right? Now if you look at here, data node 1 and data node 2, or any data node for that matter, they just know what blocks they are storing. They don't even know whether, see for example, if you take the example here, block A and P are stored in data node 1, but data node 1 doesn't know whether they are part of the same file or different file, right? They don't know that. So that means data node 1 just know that I have 2 blocks, but they don't know the mapping. Same way for other data node also. That means name node is the only one who remembers the entire metadata or mapping information. So which means if you want to retrieve, there is 100 terabytes of data which is stored on your Hadoop cluster, and if you want to retrieve all this data from the Hadoop cluster, then every client will have to go through the name node to retrieve that data, right? So basically, name node is the key point. He is the one who knows everything, mapping information. That means name node becomes a crucial process. Now we will talk about what happens if name node goes down. So if name node goes down, in the earlier versions of Hadoop 1.0 series, we had only one name node. There was no backup of name node available. Okay. In those scenarios, if the name node goes down, I will not have any other backup node which will act as a name node and support cluster, which means if the name node goes down, it will basically become, entire cluster will go down. Basically, it will become unreachable, right? So no client can access data stored on your data nodes, even though you have stored all the blocks successfully. But if the name node goes down, there is no way I can figure it out which block belongs to which file. That means it's called single point of failure. Okay, so single point of failure was there in Hadoop 1.0 series. And in Hadoop 1.0 series, there was a process called secondary name node. It was also there. Now that means secondary name node is not a backup of name node. I will repeat. Secondary name node is not a backup of name node. Okay. Why? Because secondary name node is meant for doing something else. Now you will, or anybody, even I, when I'm learning for the first time, I can easily think that, yeah, if it is secondary name node, it should be a backup of name node. So the problem is it's a misnomer. People who have given the name of this process, they gave it wrong. It actually doesn't do, it doesn't do the job which it is supposed to, for the job based on its name. It does it something else. So anyway, what it does, we will park it aside. We will talk it after some time. Right? So that means it's a single point of failure. Even though you have secondary name node, it doesn't become a name node and start serving the cluster. So which means if a name node goes down, it will be a single point of failure and entire cluster goes down. That was the problem with Hadoop 1.0 series. In Hadoop 2.0 series, what happens? They have introduced few more machines. So like you have, let's say, one more machines where you will install name node only, and it will be connected to all the available data nodes, and these guys are also connected. So what happens if this guy goes down? Another name node becomes active name node. So there is one active and other name nodes are standby name nodes. So in Hadoop 2.0 series, they have support for this, which is called name node high availability, to avoid single point of failure. So if your active name node goes down, you will have a backup of the name node which becomes active and starts serving the cluster. Okay, that's how name node high availability is maintained. Now here, what happens is every data node will send a heartbeat signal to every name node. Okay, every 3 seconds. Every 3 seconds is a default time period where each data node will send a heartbeat signal to name node. Okay. Now what happens here is, because of this heartbeat signal only, name node will know that yes, this particular data node is alive and it is being operated in the cluster. So I'll repeat again, SNN is not a backup of name node, it is for something else. So SNN cannot be a master, it cannot work as a name node, it will do some other responsibility. So right now, let's not worry about it as being a master or backup. Every data node will send a heartbeat signal to name node, and based on that, name node understands that, yeah, this node is active and I should start assigning work to this node. If it doesn't receive a heartbeat signal in that time period, then name node thinks that there is something wrong with the data node, it may be down, and hence it stops assigning any work to that data node and it consider it as a dead node. Okay, till it starts sending heartbeat signal again. So that's a communication that happens between data node and name node. And apart from that, every data node will send 10th heartbeat. Every 10th heartbeat, they will send block reports to the name node. Each data node will say that I have block B with me, I have block Q with me. This guy will say I have block A and P with me. So there is a block report which is being sent to the name node. Now there is a reason why they send this block report to the name node. I will cover that question when we understand HDFS write architecture. Okay. Okay. So what we will do now is, let us understand more about what name node does and where does it keep all this metadata information. So as you can see here, name node is actually remembering all the metadata information, and it has to keep, if there are 100 terabytes of data, it has to keep all the metadata information for all the 100 terabytes of data, right? And what it does, name node keeps all this information in the RAM or main memory of that machine. Okay, of the machine where name node is running, which means name node needs a high RAM in that machine. The machine where you are configuring name node should have a very high RAM. Okay. That's basically the use case. Okay. And approximately 64 GB of RAM is what is recommended where name node is running. And it will store, by the way, so why, there may be a question that why do we store all the metadata in memory? If we store all this metadata in the file, then what happens? Name node, whenever, see, there may be multiple clients, there may be multiple jobs which are running on the Hadoop cluster. They are called clients, right? And every job will need to process data on HDFS. Now to process data on HDFS, they need to know where that data is stored. And how do they know that? Only by contacting name node. So when they send that request, name node has to give them the response saying that these are the blocks for this file. Now, how does name node know that? Name node has to go and check that information, metadata information from the file where they have stored it. So if it has stored that information in a file, in a physical local file system, then name node, for every second, every now and then, name node has to go open the file, read the file, and then give the response back, then close the connection with the file. So there are too many disk IO calls which name node have to make if it has to do that way, and that's why it is not performance wise very good. So to avoid that, name node keeps all the metadata in memory so that any client who requests for any data access, name node will immediately look the information from the metadata available in memory and then start giving the response faster. So that way name node can improve the performance and it can save the response time. right? That is the fundamental reason why all the metadata have to be there in the main memory of the machine where name node is running. Now there is another problem. If we keep all the metadata information in the memory, right? Then what happens? If you keep everything in main memory, then also there is a risk, because if the name node goes down, then yeah, if we keep all the metadata information in memory, and if the name node goes down, then I will lose all the metadata from the memory, right? So that is also a problem, right? So if I lose all the metadata from memory, then what happens? I mean, I lose all the information of how to access this data. So that is a big physical failure. So that's the reason why, to avoid that, name node also periodically takes the backup of this metadata information from memory into the name node machine. You basically put all the metadata information in the RAM, in the main memory of the machine where name node is running, okay? And then it will start serving the clusters. Now it can serve all the client's requests parallelly. There is no problem with that. But if name node itself goes down, what happens? I lose all the information from memory, because your memory will be wiped out, right? So that is also a problem. To avoid that, name node keeps the backup of this metadata information periodically. Okay, it takes this metadata information from RAM and it puts it onto the disk, onto the physical disk. Okay, so that is why basically it actually keeps putting that information into the disk in a file as a backup. Okay, but whenever any client asks or request name node to access any file, name node will always look into the RAM only, into the main memory. It doesn't really look from the physical file. Okay, the physical file system where it keeps or store all the metadata information from memory is just as a backup, so that if name node fails, I will have a backup stored somewhere so that I can rebuild the metadata from there when it starts again. Okay. So let's understand more about this backup. Showing you this. So let's say this is where your name node is running. There is a RAM where all metadata is stored, and it has to take all the backup from this metadata into the physical local file system. It will create some file X and Y, let's say, and it stores this data in here, right? So there is a periodic interval by when it does that. So every 24 hours it dumps all the data which is there in the main memory into the physical file system. In the file, name of that file is called FS image. Okay, so this is the file which is being created, and it loads all the metadata information into the FS image file on a let's periodic basis. Let's say we are saying every 24 hours. So for now it has loaded all the data. Let's say right now it has loaded all the metadata into the physical file called FS image, and there will be some version _0. After again 24 hours time, next backup will be taken, right? So again it will take the snapshot of this memory and put it into the new FS image file with new version, okay, which will have a latest metadata in this file after 24 hours. We'll assume that way. Okay. Now in between these 24 hours also, there will be lot of action which is happening on your cluster, which means your all your processes are running, your cluster is running, which means there are many jobs which are running on your cluster. They may be writing some file, reading some file, they may be processing some data, and all of this which is happening, which is internally basically adding lot of data in the HDFS, right? Lot of jobs will, when you add any file in HDFS, what happens? It parallelly the metadata also have to be created. So name node will have to update the metadata information here and add more information about the new file which are created. If you delete some file from the HDFS, it may have to remove some file, some information from the memory, from the metadata. So there is a constant updation happens in the metadata stored in memory of name node machine to make it up to date with the cluster state. Okay. but those informations are not stored in this FS image file. Only periodically we take the backup, right? So these information are not stored. So let's say this is one checkpoint where we have dumped all the metadata into a physical file. After that checkpoint, till next 24 hours, I'm not going to take any backup. So what happens? In between also there will be a lot of changes that happens, and let's say at this point, assume at this point name node fails. So we are going to lose all the changes which are there or which would have happened in the metadata from memory, right? From the last checkpoint. So that is also a problem. You will lose that information. So to avoid that, name node will do something else. It will actually write all the changes to the metadata information into another file called edits. Okay, it's also referred as edit logs, or we can call it as edits. Okay, and that file, it will keep on pushing all the updated changes. It's just like a log file. In any application server, I'm sure you would have seen log files, just like a log file. So any changes would be pushed to the edits file, right? That's how it keeps two files. Checkpointing file, at that particular point of time, it has loaded all the data here, and then from that point, any changes to metadata to main memory will be just logged here in edits file, so that you take backup of both the files. So at this point, even if it gets failed, you have two files available which has data. But even at this point, if it fails, there is still a problem. Why? Because I have two different files. Some informations are available here, some information are available here, and these informations which are available in edits are kind of a metadata which says what needs to be edited in the original metadata. So you need to really apply this information in this FS image file, then only it will become latest file at this particular point when name node fail. Okay, so at this point, if a name node fails, then it would not be able to take the backup of another FS image file, right? So that means it will have two files, and if nobody would have merged them, then there is no latest version of FS image available. So that's why there is a separate process which will be running in the background, which is called checkpointing process. Okay, and that is where secondary name node will help you achieve that. That is the role of secondary name node. It is helping you to merge these two files on a periodic basis and create a latest FS image file, so that in case if name node fails at any point, you will still have a latest metadata backed up in your local file system. Okay.